35 years, 13 billion miles. It began in 1972 when the project started, July of 1972, with launching two spacecraft in 1977 for Jupiter, Saturn, Uranus, and Neptune.
For an odyssey spanning more than 4 decades, Voyager 1 has relentlessly pursued interstellar discovery, charting a course away from Earth and boldly venturing into the expanses of the known universe. In a recent revelation that has reverberated through the scientific community, the venerable probe transmitted a cryptic warning message, hinting at the emergence of a new elemental force within the cosmos. Michio Kaku, a luminary among the world's leading physicists, has stepped into the cosmic spotlight, unraveling the enigma surrounding this mysterious force and elucidating why it has manifested at this precise juncture in the cosmic timeline. As we stand on the precipice of potential contact with extraterrestrial civilizations, Michio Kaku suggests that signals from distant beings may grace our century. Join us on this celestial journey as we unravel the implications of this newfound force, probing the cosmic tapestry and its intricate connection to the formula that encapsulates the very essence of creation. The cosmos beckons, and the revelations are boundless. In the distant year 1977, NASA embarked on a bold move destined to leave an indelible mark on our perception and interaction with the universe. In that epical year, the extraordinary Voyager 1 spacecraft was launched, primarily designed to actively explore and gather scientific data in the heart of our solar system, with a particular focus on the outer planets and their moons before venturing into the vast interstellar space. During its mission, Voyager 1 achieved extraordinary feats, successfully performing flybys of Saturn, Venus, Uranus, and Jupiter, surpassing all expectations. Finally, it crossed the boundaries of our solar system. Now, after 4 decades, an unexpected event has captured attention. Recent readings from Voyager 1 indicate the presence of a new and completely unexpected elementary force, a tremor that has reverberated throughout the scientific community, intriguing the public. Before delving into the thoughts of renowned physicist Michio Kaku on this mysterious force and the formula that could embrace all creations of the universe, it is essential to understand the ineffable importance of this extraordinary space probe. Voyager 1 holds the record for being the farthest human-made object ever launched from Earth. Its journey began on September 5, 1977, as an integral part of the ambitious Voyager program, focused on the exploration of the outer planets of our solar system. Equipped with advanced scientific instruments and cameras, Voyager 1, in tandem with its twin Voyager 2, captured extraordinary images and data from the vast expanse of space. Among its most memorable elements is the Golden Record, a cosmic message engraved on a precious copper disc plated in gold. This extraordinary disc hosts a diverse assortment of sounds and images that depict life on Earth, from the majestic notes of thunder to the timeless melodies of Mozart, from warm greetings expressed in 55 different languages to a map that traces our position in the infinity of the galaxy. This disc serves as a time capsule, representing human culture and wisdom, and stands as an open invitation to any extraterrestrial civilizations that may cross its path, inviting them to explore and interact with the essence of our existence. The instruments aboard Voyager 1 continue to make significant discoveries during its journey through interstellar space. For example, the probe captured the first sounds ever heard from the cosmic void, a subtle yet astonishing sound generated by the vibrations of charged particles in this environment beyond our solar system. These findings provide valuable insights into the nature of the interstellar medium and the environment that extends beyond the boundaries of our galaxy. What makes the mission of Voyager 1 even more fascinating is its extraordinary longevity. Initially conceived for a mission of just 5 years, this probe has surpassed all predictions, continuing to transmit data and images far beyond the expectations of its creators. The beating heart of Voyager 1 lies in its radioisotope thermoelectric generator, RTG. This device harnesses the decay of a radioactive isotope called plutonium-238 to generate electricity. Plutonium-238 is not easily obtained, but it is produced in special nuclear reactors through a complex process that involves irradiating another isotope called neptunium-237, which undergoes subsequent radioactive decay, transforming into the precious plutonium-238. Picture this, a stack of thermocouples ingeniously arranged inside the RTG. These thermocouples, composed of different materials, generate a temperature gradient when exposed to the heat derived from the decay of plutonium-238. It's almost like a thermal celebration happening within this probe. This temperature gradient is what gives rise to an electric current through a phenomenon known as the Seebeck effect. This electric current represents the lifeblood that powers Voyager 1's instruments and systems. When the probe embarked on its epic journey, its RTG delivered a whopping power of 470 watts. Over time, and as it progressively ventured into the unknown, the generated power has experienced a gradual decrease. The half-life of plutonium-238 is approximately 87.7 years, which means its power halves every 87.7 years. Consequently, the current estimated power of Voyager 1 derived from its RTG stands at around 250 watts, a still impressive figure considering the decades of exposure to extreme conditions that the probe has faced. Recently, Voyager 1 has been involved in an extraordinary encounter that prompted the remarkable spacecraft to transmit enigmatic messages back to Earth. These unusual signals have heightened the curiosity of scientists, leaving them faced with an enigma to solve. Some experts hypothesize a malfunction, triggering a search aimed at deciphering the problem and identifying possible solutions. In this investigative process, scientists are exploring unconventional theories that are capturing the attention of the scientific community. One of the intriguing ideas is the famous divine equation. Michio Kaku, renowned theoretical physicist and professor at the City University of New York, has had a long-standing interest in this equation throughout his illustrious career. For 3 decades, Albert Einstein tirelessly devoted his research to a profound goal: to unify the 4 fundamental forces of nature, including gravity, electromagnetic force, and the 2 nuclear forces. Kaku, in his visionary approach, sees the great challenge in formulating a theory of everything, a complete equation that encompasses the fundamental principles of physics. Comparing this equation to Leonard Eule's mathematics, which elegantly encapsulates essential constants, Kaku coined the term divine equation of mathematics for this theoretical masterpiece. Now, faced with a problem with Voyager 1, we wonder if Michio Kaku's divine equation can solve it. Michio Kaku, the Japanese-American researcher, holds an influential position comparable to that of Stephen Hawking in Europe. Raised in California, Kaku developed a passion for physics and astronomy from a young age, pursuing studies in theoretical physics, presenting theses, and writing bestsellers to make the knowledge of the universe accessible to ordinary people. Kaku is widely recognized as a visionary and has achieved superstar status among physicists. In a recent interview, he examined the fascinating data from the Voyager 1 probe, raising questions about the possible discovery of an unknown force. While acknowledging the potential of contact with such a force, the question remains: could it provide a key to unify the grand field theories? However, some scientific branches argue against this perspective. The unification of field theories would be embodied by what Kaku and his English-speaking colleagues define as the divine equation, a unique formula capable of describing all phenomena and forces in the universe. The implications of such a formula go beyond our current understanding. To fully appreciate the Voyager 1 detection and the gap between theoretical physics and quantum mechanics, it is essential to understand the problem at hand. Theoretical physics deals with phenomena on a large scale, including planets, galaxies, forces, and rules that govern dynamics and interdependencies. Established theories in this field include Einstein's relativity. In contrast, quantum mechanics emerged much later and allows us to explore the subatomic realm. Technological advances have allowed scientists to study elementary particles such as quarks, neutrinos, and quanta, albeit indirectly. The effects and behaviors of these particles are observed and studied in structures like the particle accelerator in Geneva. This progress would have been unthinkable centuries ago when the view of the sky was based solely on simple telescopes. The foundations of classical physics are mainly based on visible, measurable, and experimentally demonstrable phenomena. For example, While gravity itself is invisible, its effects are observable and experienced by all, as demonstrated by the falling of an apple or the solidity of our feet on the ground. Isaac Newton, an English naturalist, was the first to define physical forces in terms of motion and dynamics. However, it was Albert Einstein who delved into the realm of subatomic particles, such as photons or quanta, in the early 20th century. Einstein, in fact, received his Nobel Prize for this contribution, rather than for the theory of relativity, as is commonly believed. During his lifetime, Einstein recognized the revolutionary nature of his discoveries, but also realized that they were insufficient to describe the entire cosmos. He tirelessly sought a unified field theory, a scientific statement that could embrace all phenomena and forces in a single formula. However, Einstein faced the challenge, rejecting quantum physics and famously stating that God does not play dice, referring to the probabilistic nature that seemed to govern the subatomic realm, contradicting his physicist's worldview. Born in 1947, Michio Kaku came into contact with quantum theories during his studies and recognized that the two branches of physics were not mutually exclusive. Kaku acknowledges the practical applications of physics since every force discovered in the past has had a profound impact on human history. Newton's work on mechanics and gravity laid the foundation for the Industrial Revolution, while Maxwell and Faraday's unification of electricity and magnetism led to the Electrical Revolution. Einstein's famous equation, EMC squared, paved the way for an understanding of nuclear power. Each advancement in physics has redefined the course of humanity. However, the challenge of uniting the two pillars of modern physics, relativity and quantum theory, is significant. Einstein's general theory of relativity, which describes the behavior of gravity in terms of smooth spacetime curves, conflicts with quantum theory, which deals with discrete particles and their interactions. This disparity makes the search for a unified theory even more challenging. Kaku recognizes that numerous brilliant minds throughout history have proposed theories of everything, but each attempt has proven unsuccessful, often plagued by divergences and inconsistencies. However, there is one theory that has withstood these challenges: string theory, in which Kaku himself specializes. String theory proposes that at a fundamental level, particles are not point-like entities, but rather small vibrating strings, similar to guitar strings. The different vibrations of these strings give rise to the various subatomic particles observed in nature. The beauty of string theory lies in its symmetries, allowing for the interconversion of particles, transforming electrons into neutrinos or neutrinos into quarks. While the theory remains consistent, Kaku believes that string theory is the only mathematically consistent theory among the contenders. Other theories tend to show mathematical inconsistencies that compromise their validity, while string theory maintains internal coherence, providing confidence in its potential as an elusive theory of everything. However, string theory faces its fair share of objections. One of the main criticisms is the lack of experimental tests, making it difficult to confirm its validity. However, Kaku remains optimistic that progress in technology and scientific understanding will bring us closer to verifying the theory. The implications of a theory of everything are staggering. It opens up the possibility of time travel, the existence of wormholes connecting distant parts of the universe, knowledge of what happened before the Big Bang, and the existence of parallel universes within a multiverse. How can the divine equation help us solve the possible malfunction of Voyager 1? Before addressing the fundamental question, it is crucial to note that Voyager 1 has already experienced an anomaly in the past. Back in 1980, the probe had to deal with a significant challenge related to its gyroscope, a critical component responsible for the stability and orientation of the spacecraft in space. This device helps define the probe's position relative to its intended trajectory and makes precise corrections to keep it on the right path. However, irregularities in the functionality of the gyroscope occurred, causing concern among mission operators and engineers. These irregularities affected the accuracy of Voyager 1's attitude control system, opening the possibility of deviations from the planned trajectory. To address this situation and ensure that the probe maintained the desired course, a dedicated team of engineers and scientists worked tirelessly to identify the source of the problem. They conducted thorough analyses, examined telemetry data, and performed simulations to pinpoint the origin of the irregularities. After extensive investigations, it emerged that the gyroscope issues were likely related to component aging and the extreme conditions of space. To mitigate the effects of these irregularities, the team developed innovative solutions. Software updates were implemented to compensate for the reduced gyroscope precision, and the attitude control system was recalibrated to maintain the desired trajectory. These efforts successfully stabilized Voyager 1, allowing it to continue its mission and provide valuable data on the outer regions of the solar system. Now, you may wonder what the connection is between a technologically dated probe from the 1970s and the resolution of the enigmatic divine equation. The connection is both clear and intricate, as scientists find themselves once again divided regarding the current data received from the probe. I will present you with the facts. In 2012, Voyager 1 reached a historic milestone by becoming the first human-made object to cross the boundaries of our solar system. Our sun emits a constant stream of particles, creating a vast bubble known as the heliosphere, which surrounds the star and its planets. Beyond this bubble lies interstellar space, the vast region between the stars. The key difference between these two zones is related to the forces at play, particularly the density of particles within the heliosphere. While the particle density is about 100 per cubic centimeter inside the heliosphere, once Voyager 1 crossed the threshold into interstellar space, this density drastically decreased to just 1 particle per cubic centimeter. This marked disparity has led researchers to hypothesize that sound transmission in cosmic space is either impossible or significantly attenuated. Sound relies on particle oscillations, and where there are no oscillations, sound transmission is theoretically absent. Until that moment, our understanding of interstellar space was based on mathematical and physical assumptions, along with observations of weak oscillations such as gravitational waves. However, Voyager 1's entry into interstellar space surprised, revealing a denser and more stable boundary than initially predicted.